cool. Wow, detect speech, that's amazing. Yeah, so I'm Chris. I'm a third-year PhD student here at C4DM. I work a lot with, DDSP and modulation specifically. So I study spectral-temporal modulations, loss functions for modulations, and just anything that's moving, so time-varying audio systems. So today I'm just going to go over this paper that I worked on. So a little bit of background, and then how do we discover modulations in a sound? That's something I was very interested in. And yeah, we don't have time to go over everything, so check out the paper. There'll be a big link for it later. So some background. The main motivation for a lot of my research back when I did my master's in sound matching work is actually Serum. I learned a lot of sound design with this synth, and this is actually Serum 1. Serum 2 is out now, but one thing that always struck me as really interesting is Serum and Vital and many other synths are all modulation centric. So how a sound moves, I would argue, is almost as important as the instantaneous way the sound is made. And I noticed through my years working on these problems that kind of the modulation of sounds is a little bit of an afterthought. People would typically, predict them just one by one. I'll show you in a second. But basically, this was the inspiration, and specifically these curves, which is how you draw modulations in a sound design setup. This is the modulation XY grid in Vital, a free, really great synthesizer. And the obvious thing here is we're well past the days of ADSR for modulations. You can draw in anything you like. And Serum 2 now actually has even crazier modulation things, like you can do XY modulations and like chaos modulations and things like that. So the idea here is, given a sound, how is that sound moving and what are the underlying modulation signals? So Ben already went over this problem quite nicely in the previous presentation. So just as a quick refresher, the synthesizer parameter estimation problem is given a sound, what synth parameters made that sound, right? There's kind of two naive ways to do this. One is you train a neural network to estimate the parameters directly. As Ben told you, this has problems with regression and estimating the expectation. A more kind of promising approach, although also has its flaws, is trying to estimate the sound. So making sure the sound matches, and that's why it's called sound matching. So seeing whether the underlying synth can match a sound, and then you'll bubble up the parameters in the middle. One thing that's nice about this project is that we use sound matching to discover modulations, but we don't actually care about the sound matching quality that much. We're just using it as a tool to find something interesting in the sound. And this also opens up a door of creative possibilities. But that's something I want to stress. This project is not a sound matching system. It leverages sound matching to do something else. So one thing that's common about synth parameter estimation systems is they typically estimate fixed global parameters. So they assume the sound is kind of this frozen patch. Of course, some of those parameters might move, like the decay on an envelope, right? But in general, they tend to output global parameters, or if there is a parameter that's changing over time, they tend to predict a high dimensional frame by frame value that has no restrictions. So it's just going frame by frame what the predicted value is. And this works quite well if you're trying to estimate a sound. However, it doesn't consider, the artistic process underneath it, or even the shape, the structure, or the routing of the modulations. So how is the synth put together by the person making the sound? And obviously, a human is not putting in every single value every 10 milliseconds of a modulation. That's not how humans create movement in their music. And so that's what kind of I thought would be interesting to look at. And so a lot of this work is inspired by this. So they kind of ignore the human sound design element, and anyone who's worked on neural systems that predict sound matching things and have frame by frame features, you'll see features like this. So if you look at the frame by frame control parameters of some sort of sound matching system, it'll typically be overfitting to extremely precise positions to match the sound as perfect as possible at every single step, right? And this is not how a human makes their this is not telling us how the underlying modulation is working. So the approach uses DDSP as a kind of technique to instill interpretability. So DDSP is basically you infuse traditional signal processing with neural networks. So you keep all the benefits of traditional processing that has strong guardrails on the audio and is efficient and interpretable. And you get a neural network to predict the parameters of controlling a DSP module. So it's a really great paradigm. It's very useful, and I'm leveraging it here for its interpretability. So basically, there's 3 steps to this modulation discovery approach. So the very first one is we have to figure out the modulation routing, and this is the one where you can be kind of the most creative. So in my case, I have a bunch of sounds made by, a synth like Serum, and I can put together a synth that is similar that will tell me something about the modulations with each module. So the way I think about it is that each module represents one kind of modulation. So I might make a synth that has a wavetable modulator here, the additive modulation, and then a filter here, like a resonant filter, subtractive modulation, and then maybe an envelope at the end for the loudness, right? Which is also kind of subtractive. This is a blurry, this is not a discrete box. These are blurry and overlap, but that's kind of the fun. So you can build your synth with these DDSP blocks and treat them as logical modulations that you would like to discover, right? And then the other thing is sometimes DDSP blocks might have a lot of, their modulation signals might be high dimensional, so they're not very interpretable. So for example, if your additive block is a harmonic oscillator, it might have 100 sine waves. And so of course they all need to change. And one trick we do here is we just reduce the dimensionality by putting them through an adapter, which is an MLP. So just to put it in words, we first choose our synth architecture, then we reduce the dimensionality if it needs to be reduced using an adapter. And this introduces an information bottleneck. All of this will reduce sound matching quality since you are reducing the expressivity of the synth, but it's always a trade-off between expressivity and interpretability, right? And yeah, so these are multi-layer perceptrons. They're very lightweight and they're causal, so they don't need to worry about, at inference time, you can use them very easily. So that's the first step, is modulation routing. Then the next step is what I've coined modulation extraction. So I have another paper on this from 2 years ago for audio effects, but the idea is very similar. There's some audio effects that are modulation driven, and you can't model them causally without knowing the underlying modulation signal. So the idea is that given some input audio that's been affected with a modulation signal, we can use a simple CNN. This is called LFONet. It's a simple temporal CNN that can output the modulation signal frame by frame. And so this can be trained directly on modulation signals, or it can be trained end-to-end. It doesn't have to be trained in a direct supervised way. But basically, it'll output a modulation signal given some input audio. And I leveraged the same technique. If you're interested in this paper, check out Mitcheltree mod extraction for the audio effect kind of parallel work for the synth stuff that's being done here. So in this kind of approach, it's very similar. We input a spectrogram. This time we don't have dry and wet since it's a synth. It's just purely wet audio, so to speak. I also extracted some delta and delta delta. This is just looking at the derivative and the acceleration of the over time of the features. This is not super necessary. I found it helps a little bit and it gives a little bit more information. But the idea is just you have a spectrogram and then a neural network that's going to output your 3 modulation signals, let's say 1 for each component that you identified during your modulation routing. So 1 per component, or it could be like 2 or 3, it's up to you. In the paper, it's always one-dimensional for maximum interpretability. And then finally, the kind of most important step is the modulation parameterization. So this is where you decide what restrictions are on the modulation signal. So we've already reduced the dimensionality, which will increase interpretability a lot. And now we're going to do one more step, which is make the modulation signals nicer to look at and more human-like. So the most naive approach and kind of the baseline would be you do frame by frame. So this is no parameterization in a sense, where, for example, if this is the dashed modulation you're trying to discover, so to speak, the frame by frame will maybe get the general shape, but it's also going to overfit and try to really get the exact match at every point. So this is with no restrictions. Then low pass filtering is an obvious step. You just low pass filter to a modulation rate of like maybe 8 hertz or 10 hertz. You know, most LFOs are less than that. So this is a very kind of no-brainer, I would say, to make it look better, right? And this is balancing expressiveness and human readability. I don't have time to go through all the experiments. So basically these conclusions are from the experiments, but you know, it follows a lot of logic as well, which is you know, the more expressivity, the better the sound matching, but the less interpretable, right? And then my personal favorite, I spent a lot of time tweaking this and making it differentiable and beautiful, which is piecewise 2D Bezier curves. I love this because it matches exactly how the XY curves are done in a vital modulator in the common soft synth. And you can do this if you're careful differentiably. So you can still train it end to end. It's quite finicky, but if anybody needs differentiable spline implementations in PyTorch, hit me up because I've spent too long dealing with this. But these are really nice because they maximize interpretability. And let's see. Okay. So overall, the entire system, you have your modulation extraction happening here. You have your modulation routing happening here. And then this is the parameterization in the middle, which is converting it to splines or low-pass filtered or whatever. And then this entire thing is trained with a simple multi-scale spectral loss. I also work on other loss functions for modulated audio, but that's a chapter for another time. So this is the entire system. And what happens is if you train this end-to-end on sounds, you're going to uncover modulations in the middle. And it's kind of fun because they don't necessarily match the modulations that made the sound. And it really depends on how you routed the DDSP systems. But you know, that was one of the interesting things is this discovery aspect of it is can it find modulations? And for example, if you make a sound, there's many ways to do the same sound with different modulations. So I found in my experiments that, you know, modulations would be converted from the wavetable to the filter or to the envelope or shared between them or some combination. Evaluating this was a nightmare. It's really interesting how to evaluate something that has no ground truth. And so if you're interested in that, check out the paper because I think we came up with some clever ways to do this. And so we then tested it on unseen, on multiple DDSP synth architectures, like some common ones like the differentiable wavetable architecture, the original DDSP architecture, and also the one that we suggested in the paper. We do this on serum audio, which is crazy because the little DDSP synth cannot recreate most serum audio, but it's meant to find some of the movement in that audio. And these are the different parameterizations, like frame by frame obviously can be very extreme. Of course, once you rein it in, you can make it more interpretable. And you can choose, for example, how many segments, you know, how many spline segments you're using or what your low pass filter is. So there's a lot of, it's like a dial you can choose of interpretability. So yeah, if you want to check it out, this is the website. There's, yeah, just the tree mod discovery. And I guess I have 5 minutes, but sorry, people wanted to. So yeah, the experiments, just really quickly, we did modulation extraction. So can the system extract modulations when we know the ground truth on a white box synth architecture? So I evaluated this on unseen vital modulation curves. Then we did on gray box synths where it's synthetic audio just to see the proof of concept. And then kind of the ultimate was highly modulated complex audio from serum and uncovering the underlying modulation signals in there when we don't know what the ground truth is. One way we did evaluate it is we use these proxy modulations by looking at spectral flatness, which is like kind of how tonal something is, spectral centroid, RMS for loudness. So there's ways you can eke out some idea of what the modulations are. And then to deal with the symmetries and modulations, I used a least squares solver too. But the details are in the paper. Yeah, so this will be presented at WASPA in Lake Tahoe in October. So I'm excited to go back to that area. And there will be Newtone plugins, which I'm also part of Newtone. So that's a platform for hosting PyTorch models in the DAW easily. So I will export all the trained synths in Newtone so you can mess around with them. things I think would be really interesting is the creative applications, because you can imagine you can just shove random audio in there and see what happens. And you can also use DDSP architectures that are really different from how the sound was made and kind of uncover interesting modulations in that sense. So I think it'd be really fun to try out unconventional inputs and synth architectures and see what kind of movement you find. And once you've learned these synths with the sound matching approach, you can at inference time feed it any modulation you like and see what it'll sound like. So it could be an interesting kind of novel modulation exploration in a sense. So not so much timbre exploration, but the movement exploration. I think the symmetry is super interesting. There's obviously tons of symmetry in the modulations as well. So, Ben would love this. And I also work a lot with loss functions. So I'm going to unleash them on this problem at some point as well. But yeah, that's it. Any questions?